Storyline 2, Lesson 10. What are the similarities and differences between 1 mole and 1 gram of hydrogen and gasoline? Let's find out. What did we do in the last class? Well, we built models of hydrogen and octane combustion. We were calculating the energy released when each bond formed and the energy absorbed when each bond was broken, because before we had counted all the bonds up. All right, time to model what we figured out. You can see that we looked at per gram, we also looked at per mole, and we looked at hydrogen, and we looked at octane. So now let's find a way to represent energy in each of these situations. Okay, well, first of all, was energy coming in or was energy going out? Yeah, it was combustion, so energy was going out. Yes, some energy had to come in to break bonds, but more energy was released, so it was exothermic. So the overall change is energy comes, okay? So let's just switch this color. All right, so for hydrogen octane per gram and hydrogen octane per mole, energy is going to be coming out. But the same amount was not coming out. Hydrogen per gram, right, had a huge amount coming out. So let's represent it by this very large arrow, right? Per gram, right? A lot coming out, right? When we look at octane per gram, it still has energy coming out, but not nearly as much as from hydrogen. Okay, so that's a comparison between the grams. Now, what about a comparison between the moles? Well, per mole, hydrogen had less energy going out than octane did. So octane has the big arrow of energy going out. Okay, so now what I'm going to do here, down here, the arrow equals, and I'm going to do this because when I look back at my notes later, I may not remember. So our model shows that hydrogen releases much more energy per gram, but octane releases much more energy per mole. Okay. So let's review. Hydrogen only has 2 atoms and 1 bond. H, H, bam. Octane has a whole lot more atoms and a whole lot more bonds. Hydrogen released more energy per gram. Octane released more energy per mole. So we need to know the difference between a gram and a mole. So we know that we measure grams with mass, right? But what about moles? Why might it be important to measure in something other than grams? Well, maybe grams are too small. Maybe we have to use something different when we have a lot of something. Maybe we should compare 1 mole of 2 different substances and see if we can identify any differences. All right, so here's a mole of sugar and a mole of salt, and one salt in particular, NaCl. Okay, so what I want you to do is take a moment in your notes and record some observations of the mole of sugar and the mole of salt. Here is a little bit more information that you can add to your observations. This right here is the mole of salt on the balance. Here is the mole of sugar on the balance. All right, so let's go over some of these observations. You may not have them all, and you may have some that I don't have. If you don't have the ones I'm going over, add them to your list. So they were both white, solid, could even say crystals. From the video, it's a little hard to look closer. For the mole of salt, it had less volume. It took up less space. There was less of it, right? And it had less mass. For the mole of sugar, there was more volume, more mass, and those are the specifics for the mass. In fact, I had to use a bigger container to hold the mole of sugar. So, what do you think the relationship between moles and mass might be? Remember, this is one of those times when there isn't a right answer right now. You're making a prediction. What do you think? Okay, so write your answer on your paper. All right, let's investigate salt and sugar a little bit more. You have this chart right here in your notes, and I want you to record some observations that you notice about a mole of salt and a mole of sugar. Okay, here's some information about both. Okay, let's go over some of those observations. Again, if you have things that I don't have, perfect, beautiful. That means you used your eyes and your observational skills, outstanding. If something comes up on my list that you don't have, add it. So for a mole of salt, there were less atoms, literally 2. Less mass. You could give the specifics of the number. It had the same number of particles. It had 6.02 times 10 to the 23rd particles. And the particles are different sizes. So you can see the green one and the purple one are different in size. There are also bonds. You may have said that. Now, for 1 mole of sugar, there are more atoms, like a whole heck of a lot more atoms. There's more mass. You could have written the specifics. The same number of particles in a mole, and you could have written the exact number, 6.02 times 10 to the 23rd. Seems like that number might be important. We should probably remember it. And the particles are different sizes. It's a little hard to tell on the squished down image, but those particles are not all the same size. Now let's take time to link the ideas of mass and mole away from sugar and salt and back to our fuels. Okay? So similarly, how you had a chart about a mole of salt and a mole of sugar, now you have a chart about a mole of hydrogen and a mole of octane. Here I want you to record similarities that you see and differences that you see. All right, let's go over. So for similarities, again, they have the same number of particles in a mole. At 6.02 times 10 to the 23rd again. Interesting, okay? They both have hydrogen in them, okay? Some differences. Well, they have a different number of atoms in a particle. So hydrogen has hydrogen, hydrogen, bam, connected. And then octane has 8 carbons and then all these hydrogens around. They have different masses and the particles are different sizes. Okay, but in hydrogen, the 2 particles are the same size. When we look at octane, the carbon and the hydrogen are different in size. So the octane is a much bigger molecule and hydrogen is much smaller. The mass of 1 mole is called molar mass. Now that's logical, that makes sense, right? But it's also called gram formula mass, meaning the number of grams in the formula, okay, or just formula mass. So that you have to remember that mass is grams, and so the grams in the formula, okay? But let me show you how to calculate it. So as I do this here, you are going to need to add this to your notes, okay? What we need now is information from the periodic table. Okay, so here I looked up carbon and hydrogen. Why did I look up those 2 elements? Well, because carbon and hydrogen and then just hydrogen are here in the formula, okay? Now where I'm going to look, and if you look on the periodic table, you'll see the key tells you This is atomic mass. Makes sense. Now we're going to tie this in. Okay, so that is the mass we're going to use. All right, so here I have hydrogen, right? What is its mass? Well, that's a whole lot of numbers. Now, you can absolutely do the math with all those numbers, but we can make it easier and round to one digit after the decimal. So I have 1, 0. The next digit is a 0, so it's just 1, right? 1.0, but I can just write 1. And how many hydrogen atoms do I have? Well, that subscript tells me times 2. So what's 1 times 2? Well, this is real basic math, right? So that's 2 grams per mole. And that's the units for gram formula mass or molar mass, the number of grams in the formula or the number of grams in a mole. Because with this formula, as it's written, we're going to be assuming that's a mole. All right, now let's do this one. Now we have 2 different elements. So we have carbon and we have hydrogen. Well, we already knew that hydrogen's mass is 1, but how many hydrogens do we have now? Yeah, 18, right? So what's 1 times 18? Well, that should be easy, right? Now carbon, let's look at carbon. Now remember I said you have to round to one digit after the decimal. You could use all the numbers, that's fine. So 12.0, okay, so there's the first digit after the decimal. Look at the next one, it's a 1. Okay, so I don't round up, so it's 12.0 or just 12, right? And how many carbons do I have? 8. So what is 12 times 8? So that is 96. So carbon has a mass of 96 grams per mole in that formula, and hydrogen has a mass of 18 grams per mole in that formula. I don't want to know the mass of the carbon part or the mass of the hydrogen part. I want to know the mass of the whole thing. So what do you think I do with those numbers? Yeah, I add them up. So I have to add 96 plus 18. So I have to do 96 plus 18, right? And what does that give me? So that's 14, 114, and then my units, don't forget units. We don't want to leave numbers naked without units. That's embarrassing. 114 grams per mole. So after we've been working with mole, how could we define a mole? Well, remember I was saying I noticed a mole was always 6.02 times 10 to the 23rd particles. In fact, it's based on a special kind of carbon called carbon-12, which we'll see in a little bit. Moles of particles that are different will have different masses. So a mole of hydrogen had a mass of 2 grams when it was a mole, but a mole of octane had a completely different mass for the mole. So the mass of a mole depends on the mass of the atoms in the particle. A mole of hydrogen only has 2 hydrogens bonded together, but a mole of octane has 8 carbons with all kinds of hydrogens bonded. Okay, a mole is a counting unit. It tells us how many particles. Like a dozen means 12. A pair means 2. A mole means a much more complicated number. It means 6.02 times 10 to the 23rd. So if I say, oh, I have a mole of oxygen, you say, oh, I know you have 6.02 times 10 to the 23rd particles. Okay, it's a special number called Avogadro's number. And where it comes from is it tells us exactly how many particles are in exactly 12 grams of carbon-12. And on your periodic table, the key at the top says carbon. So you should always remember it's based on carbon. Okay, now, something else I just want to remind you of is when you have a mole of something, the mass is going to depend on what substance you have. When you have a mole of copper, your mass is different than when you have a mole of carbon-12, okay? let's try and make a model together. So when we have a gram of NaCl versus a gram of sugar, okay? So let's think about it. When we have a gram of NaCl versus a gram of sugar. Now, I'm not going to want to show the particles bonded. I'm just going to show representative size. So I know when I'm comparing a gram of NaCl and a gram of sugar, the particles of NaCl are smaller when I compare them to the particles of sugar, right? So in a gram of NaCl, I'm going to have, and I'm trying to draw these roughly the same size, okay? I have a lot more particles, okay? And the number doesn't matter so much. We're just doing a model, so a representation, and I'm going to have a lot. And then when I have a gram of sugar, since there's so many more atoms and the molecule is much bigger, a gram of sugar has much fewer molecules. Okay, so again, I'm not worried about the number. The representation here shows the particles are smaller for NaCl, so there's going to be more of them in a gram. And for sugar, the particles are larger, so there's going to be less of them. Now, what if I had a mole? Now, I'm not going to draw 6.02 times 10 to the 23rd. That's a little wild, so let's just draw 6, okay? So if I had a mole of NaCl, I would have 6 particles, right? If I had a mole of sugar, I would have 6 particles. So that gives me a way to compare things because I have the same. So I have 6.02 times 10 to the 23rd if I have a mole of NaCl, and 6.02 times 10 to the 23rd if I have a mole of sugar. All right, let's practice with some questions. Which of the following statements is true about a mole? Well, yeah, it has literally all of them. Yes, it is the counting unit. Yes, it is equal to this number of particles. And yes, it is equal to that. Remember when we looked at the box in the periodic table? It's atomic mass. Since carbon-12, this is how I say this. Carbon-12. Since carbon-12's molar mass is 12 grams, 48 grams of carbon-12 atoms would be how many moles? Well, you should maybe be able to see the math, but I'm going to show you. So 1 mole, right, is 12 grams. So let's set up a local ratio. I don't have 12 grams. I have 48 grams, right? And I want to find out how many moles that would be. And why am I setting it up like this? Because cross multiply, I don't know, you are all brilliant at cross multiplying and can do it just fine. So 1 times 48 is just 48 equals 12x. How do I solve this? Divide by 12, right? So what should it be? It is 4. Okay, CH4, which is methane, has a molar mass of 16. What is the molar mass of each element in the molecule? Okay, so carbon, do you remember we looked it up on the periodic table, but let's go back to it. There we go. So carbon right here is 12. So the molar mass of carbon is 12 grams per mole. And what is the molar mass of hydrogen? It is 1 gram per mole. Now, in the substance, methane, I have 4 hydrogens. So in methane, the molar mass of 1 hydrogen is 1, but the total mass for hydrogen is 4. Okay. Water is made up of 2 elements, right? What are those elements? Well, H and O, right? What is the molar mass or the mass of 1 mole of each element? Well, I need to see the elements, right? Okay, there they are. So for hydrogen, it is 1, right? gram per mole. And for oxygen, now remember, what did I say? Round to one digit after the decimal. So I want this digit, but I go to the next one. That 9 says I have to round up. So I round up and it becomes 16.0 or just 16 grams per mole. So what is the mass of 1 mole of H2O? Well, I have 1 oxygen, that's 16. Each hydrogen is 1, but I have to multiply by 2, right? And then this is the mass of the hydrogen part. This is the mass of the oxygen part. Add them up, and I get 18 grams per mole. Okay, hopefully it's making sense. All right, Janaya was calculating the mass of her favorite rocket fuel, hydrogen peroxide. I don't know, that's just her favorite. She wants to use some of it in a devil's toothpaste explosion, but she needs to do it safely and have accurate measurements. Check her work to ensure she has the proper amounts. So this is her calculation of the molar mass of hydrogen peroxide using the periodic table. So she said for hydrogen, its molar mass is 1 gram per mole. For oxygen, she said it was 16 grams per mole. She said there are 2 atoms of hydrogen and 1 atom of oxygen, multiplied them here, okay, and then added it up. Are her calculations correct? Well, it should be no. Why? Because look at the formula for hydrogen peroxide. It is H2O2. So this should have been multiplied by 2. So this should be 32. So this would be 34. Okay, so she missed that subscript. Now we have a better understanding of a mole and a gram. But we need to figure out how this relates to energy output from a mole and energy output for a gram. Then we'll be ready to move on.